Was that? Okay, there we go. A little technical difficulties. I just want to talk for a bit to make sure my mic is not going to turn off. I did Windows did a big update. So maybe it'll fix the issue I was having with my mic. If it doesn't, I just want to make sure it doesn't cut out. So I'll just talk for a bit. Hey everybody, how's it going? Hope you all are doing well. I don't really know what we're gonna do today. Because, physics, lol. Okay, that was a bad intro. I kind of know what we're gonna do today, but some of this stuff I've done a little, like, it's been a bit. It's been a couple weeks. So I think I know what we're doing. Alright, so it's chapter 17. So we're gonna be doing, I think, some interference and standing waves, and then yeah, no, not standing waves, I lied. We're gonna be doing standing sound waves. Ugh, ew. I don't even know if I did problems on that before, but we're gonna do that now. Interference in one dimension, interference in multiple dimensions, and then beats. So that's just lots of formulas. So we'll start with that, and then we get to do light and stuff, which is much more exciting. Just find Christina King's linear algebra playlist. Pretty crazy? Let me check it out. Let's see. Christina King. I miss linear algebra. Okay, I searched that and that is not there we go. It was some random other person. Ooh, wow. Oh my gosh, Princeton. Wait, Princeton. This looks really cool. Oh, this is all chillin'. This is chillin'. Let's see, I haven't done inner product. Orthogonal decomposition? Have I done that? Maybe? I have not done least squares problems. I have not done that, but I assume that's just, like, we were doing that last time. I think it's just an application of stuff, which is probably why we didn't do it in my class. Orthogonal sets, we did talk about that. I think I've done all this. A little bit. We did some more other stuff as well. Like, we had to kind of take a... Oh, that class is, like, kind of, like, all over the place in my brain, because, I did it for half a year, and then I did differential for half a year. And differential, we had to do, like, a lot of other stuff. Like, we had to learn multivariable a little bit. It was a good time, though. I liked that course. I thought it was worthwhile. Maybe we can do, if I get through some of this stuff, maybe we can watch some of those videos together. Oh, okay. Let me see what problems we're actually gonna be doing from these. Let's see. It is in the syllabus. Go. Start with 17. Okay. Alright. There's a lot of problems. Not looking forward to that, but that's okay. That's kind of what physics is. I'm kind of sad because, like, my physics is more boring. I'm gonna be honest. It is definitely more boring than it was in my high school So I'm kind of hoping next quarter will be a little bit more interesting. Yeah, I don't know. It's just a shame, because, like, our labs were, like, very stimulating and, like, 15, 23... 25... 27... 30, 33, 35... Lots of problems today. 36, 39, 51, 66, 69, 72. Okay, we're not gonna be doing all of these because this is a lot, but we're gonna be doing some of them. Let's start with 2. So, okay. So there's one in here on superposition. Oh, hey, Jimmy. Ugh, I kind of don't want to do the superposition one, but... Actually, that's okay. We can do the superposition one. This is kind of a good... We'll do it this way. Okay, so there's two waves. We'll have a red wave here. I should probably draw some graph marks here. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we'll have a red wave from 0 to 4, peak at 2, and then we'll have the other one from 6 to 10, peak at 8. So this wave is going, oops, make that a different color, I lied. Did I say this one? No. Yes. So this one is going this way, and this one is going this way. Alright. So they're both moving at 1 meter per second, and this is a snapshot graph. So we're kind of gonna draw like a history graph, but on a snapshot. So this one's gonna be here, and this one's gonna be here. And since it's 0 plus 0, right, that's still going to be 0. Then we get to here. And here. And this is going to add, right, these two things. Oh, you have a question? What's up? So I'm going to draw this like, kind of like this, I guess. Can I explain spring harmonic motion? Yeah, I can totally do that. What part about spring harmonic motion? That is something I can 1000% do. I guess we can kind of talk about, like, the basic idea of an oscillation. Sure, yeah, we'll do that. Okay, so let's say you have a mass. It's on a spring, right? And this is its equilibrium position. So the way that we describe, you know, anything about springs, whether it's spring force or spring potential, it's all about, like, whether or not it's at this equilibrium, like how far away it is from this equilibrium point, right? So that's our, like, Fx equals negative Kx, which is, this is the spring constant. Delta X, we'll call it. And then, you know, US for spring potential, or sometimes it's called UE. That's our 1/2 kx squared, right? So this x is based off of the distance that this is. So we know that if we pull this, right, let's say you take it and you pull it all the way out here, this is some delta x. And this is actually, we're going to call this value of delta x A, because this is the greatest that the spring goes out in this direction. So we pull it, we take here's our hand, we're holding it, and we've pulled it, you know, out this far, and we're gonna release it. So it's gonna go all the way back, right? Because there's force from the spring. We know that the spring force, if this is our like free body diagram, we're doing an F applied, and the force that's holding it in the other direction is the spring force, FSP. So we know that it's gonna, when we let go of this, it's gonna be pulled back this way. So it gets pulled back this way, it goes all the way over here, right? And it's gonna land at that same amplitude. It's gonna go all the way over here. Sorry, I don't wanna get it. And the spring is gonna get really squished up. And then when it's at this point, now we know that like this is our new delta x. So our spring force always points towards the equilibrium, and it's gonna keep going this way, and then it goes all the way to this A, and then it goes all the way back, right? So it's gonna oscillate back and forth. And if we don't have friction, right, so if this is a frictionless surface, and we don't have damping, you know, like nothing about the spring says that this oscillation is going to stop eventually, this will just continue oscillating forever. And the way that that looks, right, is we get a type of sine curve, right? A funky little guy here. Because as we get to this point, out here or back here, you can see that our, we know that our like KE is, you know, 1/2 mv squared and all that. There's a lot of inverse squares. So we know that it's not just gonna be like a straight line like that, right? There's some sort of slowing down involved and speeding up. There's an acceleration. So this is what our sort of, you know, position, if you want to say like our if this is our time and this is our delta x, then up here, right, at the farthest we go, this is A, and at the lowest we go, this is negative A. And we're saying that we either start at 0 or we start at, usually what we say for these is that we've pulled it out, right? So normally we use cosine, right? Because our cosine starts up at 1. So we usually use a cosine graph for this, and that's going to look like delta x equals cosine of a cos omega t plus xo or whatever, right? So we have some cosine to describe that, and this is an equation that you can get a couple different ways depending on the problem, which doesn't really matter, but just know that like there is an equation to describe this. But I think the more important part when considering springs is the energy, right? So we know that our position graph is going to look like this, and we'll just say that at this point, we'll say that t starts at like 1 or something, right? So we've pulled it out, right, and it's gone through an oscillation, it's coming back. So we'll just use this because I drew a sine wave, so it's fine. It's just shifted over a little bit. Or we're defining like when it hits here is t equals 0. It's fine. So if we want to think about the energy, the two kinds of energy that we have in this system that are going to be, you know, playing against each other are, we definitely have kinetic energy, right? Because the spring is moving, the block on the spring is moving. And we need to have some sort of other energy, right? Because you can't have kinetic energy without, you know, something putting that in. So we're going to have our spring potential energy. So at this point, right here, right, when we're at the amplitude, and the block is, right, if we take the derivative here, or if we just, you know, look at this and we say, okay, what's the slope, right, from a position versus time graph, that's going to give us our velocity. We know that at the amplitude, we're going to have kinetic energy equaling 0, which means that we have to have total potential energy up at this point here, right at the top of that, thing. So what that looks like, right, is when the spring is stretched all the way out from equilibrium, we're going to have only potential energy. Then if we go here, right, well, our potential energy is based off of this distance x from the equilibrium, right? And this right here is our equilibrium. So in this case, delta x equals 0. So when we're here, when we're right at that equilibrium point, when we're moving past it, we're going to have us equaling 0, and we're going to have the maximum kinetic energy. And that keeps going, right? Now, if you were to have friction, right, or if you were to have damping, which is a concept that just says, you know, when we look at a spring and we do an oscillation in real life, that's not a perfect oscillation. There's some energy that gets lost because, you know, through oscillation, not just through friction, like the spring moving and stuff. So what that would look like, right, is every single time this block goes out, it's going to come out a little bit less far, right? So there's not going to be as much kinetic energy. We're losing that kinetic energy. It can't go as far. So it's going to be like here, and then it's going to go here, and then it's going to go here, and it's going to go here, and eventually, right, we stop oscillating. So what that would look like as a graph is we have our normal, you know, this is our normal oscillation. Wow, that's not a very good drawing. That's a little bit better. Here's our normal oscillation. But what our damped oscillation, or if you had friction or something else, right, it would look like this, where your amplitude is getting smaller, smaller, until it eventually stops. And if it was damping, then this is like a logarithmic thing, but that doesn't really matter. The whole concept is just that, like, we do have situations where there is energy loss, but if there's no energy loss, then we can describe it just like this with a cosine function. And I'm pretty sure, let's see, I'm pretty sure it's omega, yeah, which is the thing I wrote earlier, which is x of t, right? Because we want to use the time to find it. It's going to be a cosine, because this is just like in math, you know, we set the amplitude of a sine or cosine wave by putting that number in front of it. Omega t plus phi 0, which is just, this is just something that tells us, like, where in our, like, time frame are we located at? Like, is t0 equals 0? Is maybe we're shifted over here where it's like the amplitude is at the top. This just locates it in space, and then this omega is our angular acceleration, which is it's not the angular acceleration. It's 2 pi f for frequency, or you can say 2 pi over t, which is related to, like, the period of the motion, right? So how many times are we doing this in a second? How fast is this oscillating, basically? Yeah, I hope that helps. I do have a bunch of, like, worked through questions on this because I was doing simple harmonic oscillators earlier this quarter. So if you want me to send you those, I can totally send you those. Can you work this out? Y cubed plus x cubed plus y cubed plus z cubed equals k? Isn't that just, I mean, isn't that just a sphere? Wait, is it a sphere or is it a cone? X cubed, I think it's a sphere. Wait, cubed? No, that would be squared if it was a sphere. What is that? Shape? Oh. It's just kind of weird. It's like an onion, kind of? Wait, let me see. Let me put it in GeoGebra. X cubed plus y cubed plus z cubed. Oh, it might not let me. Oh, okay, it doesn't show anything. Dope. I don't know, it could be like Unreal, I guess? Or maybe I need to set it to a number. I don't know. Let's see. Yeah, no, I don't know. Can't do it, sorry, it doesn't exist. Alright. I don't want to do this graph thing. This is stupid. I know how to do a graph. We don't need to work out that. Alright. Okay, let's do something real. Let's do some numbers. There you go. Alright, standing waves on a string. Okay. Okay. Perfect. We have a little standing wave here. I'll draw it in maybe a little bit of an easier way to understand. 1, 2, 3, 4, okay. 1, 2, 3. Whoops, 4? And then we'll do the 1, 2, 3, 4. Okay, so we got 4. Oh, k being all the numbers from 1 to 100. Oh. Like a sum of n, like x cubed plus y cubed plus z cubed equals that? I don't know how I would do that. Or just like for each one? Wait, it's a system? So like 1, 2, 3? Like that? Can I do that? Wouldn't that just mean 1 equals 2 equals 3? Because if you were to substitute, like if it was this, like if you were to substitute that in, 1 would have to equal 2. I don't understand that. I don't understand that one. Not the math category? Bro, I think you're in the wrong stream. Oh wait, am I in math? I thought I switched it to physics. Am I being silly? I switched it to physics, yeah. It's 42? Cool. Okay is 42? I'm in the physics category, bro. I don't know what to tell you. Unless I didn't update my... Did not click done. Yeah, I'm in physics. I don't know what to tell you. I'm the only person streaming in physics right now. Yeah, I don't know what to tell you. Anyway, this is oscillating at 100 hertz. We've got 4 antinodes. Lovely little antinodes. Okay, so, oh god, do I remember how to do this? Okay, we need to figure out, so the fundamental frequency then is 25 hertz. Right, so like for each antinode, this is the F1. So the question is asking, how many antinodes will there be if the frequency is increased to 200 hertz? So if we increase it to 200 hertz, we're gonna get, right, 200 divided by 25 equals 8. So 8 antinodes. Let me make sure that's right. I'm pretty sure it's right. If it's not 8, I'm gonna be very confused. Although I have not, again, I haven't done this for like 3 weeks. Ugh, it's been a while. Kind of wild that I have to do this. Honestly, I was really surprised we have another midterm so soon, because like my math, we did like a whole chapter. But like we haven't even finished. I guess technically we finished 33, but kind of stop and think questions. 17. Yep, okay, it's 8. Awesome. If the tension is increased by a factor of 4, what frequency will the string continue to oscillate as a standing wave that looks like the one in the figure? So if we say, if we increase the tension, Ft, up by 4, then let's just change this. Ft equals 4 Ft. Okay, we need equations. We need equations, size, sadly. Where are they? This one. Okay, it's not loading. Awesome. There we go. All right. What is this? We gotta check V by tension. Okay. So we're gonna look at how much the frequency changes, and then we'll go from there. So V equals the force of tension over the density. Density is not changing, right? So we change this to 4Ft. We're gonna get 2 times VO equals V1. That's our new V, this is VO. Right, because square root of 4, 2. We've got two times the speed, so now we have to do V equals lambda F, I believe. Yeah. Or do we not want lambda? Do we want... We probably want Fm equals V over 2L? Yeah. It's pretty much the same thing as that. But we'll use it. So F, we're looking for F1 equals, you know, V over 2L. Now we have F1 prime equals, sorry, my convention's a little, we'll change this to V prime. It's V. So then we have 2V over 2L. So F1 prime equals 2F1. Okay, so we got that. That means that the fundamental frequency is 200 hertz, it's 50 hertz. So if we want 4 nodes, then we need to have, we want 4 nodes, then we need to have 200 hertz. Pretty sure. 200 hertz, baby, let's go! Okay, I still got it, It's been a while since I did antinodes. It's fine though. Oh, it's fine. Carnage, wrecking. Knocking over stuff. I'm just so excited about the antinodes, guys. I swear. Alright. Nice, we've done one problem in 30 minutes. Dude, that's worse than my math class. These aren't even that hard. Oh, okay, whatever. All right. 11. What is this? What are we looking at? What have we got, Captain? What have we got? Oh, I've done this one. Okay, it's fine. We'll do it again. A heavy piece of hanging sculpture. That means I get to draw a sculpture. What should the sculpture be? I think it should be chat. Let's draw a little chat. What's chat gonna be doing? Laughing. There's chat. They're so excited. Yay! Happy chat. Hanging in the breeze. Like a piñata. Oh god. Don't worry. The sculpture is suspended this way. Like a little backpack. And a belt. Okay. Spending too long drawing that. Anyway. It's suspended by, so this is 90 centimeters long. Let's change that to a meter. And it is 5 grams. Steel wire. When the wind blows hard, the wire hums at its fundamental frequency of 80 hertz. So F0 to F1 equals 80 hertz. What is the mass of the sculpture? Okay, I did this question before, but I don't remember if I did it on stream. I don't think I did it on stream. So we have to draw a free body diagram, everybody. MG FT. So we need to find the tension in this string by reverse engineering to get the other stuff here. So the first thing we want to do is, I don't know, we could do this a couple different ways. The first thing I'm going to do is look at, so we know that we want to get here. We have this value. We don't know this. We want that. Actually, let's do this. Let's do that. So we have this value. We don't have V, so we need a V. And we can get V a couple different ways. We could try and do, you know, lambda, but we don't really have a lambda. So I think the faster way to do it would just be F1 equals V over 2L. So we have 80 hertz equals times 2 times 0.9 equals V. So that's going to equal a number that I don't know off the top of my head, because I could be psychic. Could be psychic. I'm not. Also, I don't think psychics can do math in their head, necessarily. But whatever. 144. And we're all clear on the meters, because we converted stuff. So now, all we gotta do is pop this in here. And we are good to go. You know what, let's move this up. Why am I taking up so much space here? Let's consolidate, baby. There. Nice. Okay. So we've got our density. This is our how much mass per the area, or like the length, right? So we know that it's how much mass? 5 grams over 0.9. I think it's M over L. Yeah. We've got 5 over 0.9 times V squared, which we could be really fancy if we wanted to and do 80 times 2 times 0.9 squared, and then cancel this out, then cancel this out, and make this 0.9 over here, and just do 80 times 2, and then we'd have 5 times 160 times 0.9, which is kind of fancy, so I'll do it that way. Because it means less plugging in numbers. No, 160 squared. Shit. And that's why you don't do that. But whatever. That seems like a lot. That seems like a lot. Oh, it's because it said 5, did not turn that into kilograms. Okay, 5 grams, that's, we got a thou. We got a thou of a kilogram. 5 thou. 0.005. That's a lot more reasonable. I was like, that's a really large number. It's not that. 0.005. Yeah. 115.2. That's still a lot. Equals mg. And we're looking for the mass of the sculpture, actually. So we need to... This is in newtons. So we need to actually divide this by gravity, even. Divided by 9.8. 11.75. Wow. 11.75 kg. Let's see if that's right. Let's see if that's anywhere near right, even. It's 11. Hello, 12 kilograms, baby, that's close enough. This book rounds a lot. This book rounds a lot. But yeah, we did it. That was a good one. I like that one. It's, you kind of have to think about it. You kind of have to think about it a little bit. Kind of have to do a little thinking, a little pondering even. Okay, 15. What do we got? What have we got? Something new. Something seems not easy. Yeah, so this is like the physics that I was used to, where a lot of it was like, okay, you have a point A and you have a point B, and you have like 4 equations like in the middle, and you have to figure out how to connect them to get to the other point. And like that was why I liked physics, because it was kind of cool to like, oh, I need to get this value to like put it in here, and then this value like becomes full, and like we can put it back in here and with another value, and then we get another value, and this is a really exciting value. Yeah, I don't know. But this is like, a lot of the questions from this book are really straightforward. Like really straightforward, and it's like, aw man, come on bro, I don't want stuff that's this straightforward. That's kind of sad. Ooh, this is exciting, this is exciting. Alright. We get to have an open tube. Chat, we haven't even done tubes yet. Chat, you guys haven't done tubes. We haven't even had a little tube. Alright, so tube is filled with an unknown gas, and this is 80 centimeters long. There's some gas in here. That's my gas. That's the gas that I'm drawing. Just pretend that that's gas. So the frequency is 500 hertz. That's not a 5. Failed step 1. We've got the molecules going this way, which is kind of hard to draw. I don't really like drawing longitudinal waves. So we're trying to figure out the speed of sound in this gas. So V sound. So how are we going to do that? Well, let's look at our equations first. We've got a couple little things here. So if we had a temperature, right, we could figure it out that way. Or open, where am I open to? I think we gotta do it with a little frequency here. It says a standing sound wave, right? So, oh shit, we gotta figure out how many nodes there are. Okay, it actually shows, I didn't draw this completely right. There's another one here. So, what this is saying is that there's two molecules that are staying in the same place. So that means we have 2 antinodes currently. Because antinodes are like wait, no. Are the antinodes the big ones? Am I tripping out? Let me make sure. The antinodes are the big ones. Fuck. We have 2 nodes. We have 2 nodes, chat. We have 2 staying the same molecules and 3 moving ones. But we don't care about the moving ones. We only care about the staying the same ones. So, to find our fundamental frequency, which is what we need, or I guess we kind of don't, but I feel like it's less work to do it with this, because then we get a 1 in the next equation. So to find our fundamental frequency, easy. Bam, divided by 2. 2 nodes. Okay, divide that by 2. Alright, we got our fundamental frequency. Now we plop this guy in here, V over 2L. And look at this, so easy. V equals F1 times 2L equals 250 hertz. I don't need to write hertz. 250 times 2 times 0.8. And then we're gonna figure out the speed right here. And this kind of conceptually makes sense too, because we know that like 250 times 2 is like 500-ish. And that's like kind of close to the speed of sound, like it's in the same order of magnitude. So, you know, we're chilling. And look, 400. That's like, you know, the speed of sound is in air is 343. So that's not too far off. So that's a pretty good sign, probably. Let's see, is it 500? 400? What did I say? 400, exactly, on the dot, baby. Oh, beautiful. So yeah, if you have a tube filled with gas, filled with an unknown gas, you can make sound go faster, or slower, or do whatever. You're a master of your own world. So. It's, yeah, I don't know. Standing waves I feel like are really, really, really specific. I mean, they're super useful. But it's such a small part of the entire world that we study for a longer time than I feel like it should get. But, you know, whatever. Alright, what are we doing next? 17, I think? Nope, 23. Alright. Ah, interference in one dimension. Okay, we gotta do some trig here, chat. Probably. Ooh. Ooh. I don't like that. Ew. Ew. Okay. Well, yeah. Well, whatever. Okay. We're gonna pretend that none of this is about sound. We're gonna pretend that... Because, like, sound waves... I mean... We had like a whole massive discussion about this in class. I don't really know why. It's really simple. Basically, if you have a speaker, right, the way that sound is made, the way that like my mic is picking up and putting out sound, it's vibrating the air back and forth like this, right? Those are longitudinal waves. If you have two speakers like this, and these are longitudinal waves going back and forth like this, they don't combine the same way as if you had a source that was sending out transverse waves. Because these are in the same plane. And these can like add up, right? Like whatever. But these like jumble up and go all bonkers. So we're just gonna, anytime it says speaker, I'm just not gonna say speaker. So it doesn't really matter because I'm not gonna say it. So whatever. Anyway, we have two sources of waves along the x-axis. And the room is 20 degrees Celsius. The room is 20 degrees Celsius. And they are emitting at 686 hertz. If the sources are in phase, right, so same phase constants, phase constant 1 equals phase constant 2, what is the smallest distance between the sources for which the interference of the sound waves is maximum destructive? Okay. Alright. What we're trying to do is we're trying to, right, so they're emitting sound, whatever. They're emitting waves that look like this. We're trying to have them line up perfectly oppositely. Like this. Like that. So they cancel each other out. Because if we do this and we add this value and this value, that gives us straight line, baby. So we want no waves. We want 0 waves. But the way we're going to do that is by changing this distance here, delta x. So the way that we do this is kind of interesting. Let me see, what do we need? Destructive means that the difference in phase has to be like a half a number, like a half a wavelength, or half of a period, or half of a, what is the other one called? Either wavelength or, yeah, half a period. It's gotta be out of sync by half, exactly. So I think it's this one. I think it's this equation, which is delta, like the difference in phase, right? So we want this to be, in our case, the easiest way to do this would be to set this to 1/2. Right, so if one of them is here, right, the other one is just half further. So we got difference in phase equals, so 2 pi delta x, which is our distance we're moving, over the wavelength, plus the distance in our phases. But we know that the distance in our phases is 0, so we don't really have to deal with that. The things we do need to find, we're trying to find delta x, so what we'll do is we'll just say 0.5 lambda equals delta x over 2 pi. Now all we need is lambda. A couple different ways we can get lambda. I think the way that we're gonna do it is kind of nasty. Kind of a little bit of a nasty boy here. And so v equals lambda f, right? We have a frequency, so we're chilling there. Just gonna do lambda equals v over f. We're chilling with the frequency. But we don't have a speed. And since they specify a temperature, we're gonna have to use an equation to v equals 331 plus 0.6 times 20. Yeah. It's just plug and chug. I don't know what else to tell you. We didn't prove this. This is just something that exists. Oh, that gives us 343. The answer, okay, it's the same thing. Cool. That's funny. Anyway. So if the room is 20 degrees Celsius. Wait, 20 degrees Celsius? Isn't that really cold? Or is that like, no. What is it? Wait. 20 C to F. No, 68. That's not cold. That's like normal. Well, it's like a nice day. Okay. 20 Celsius is hot? Yeah, I guess that could be a little hot. Could definitely be a little hot. I don't know, I was just thinking about like on a scale from 0 to 100, which is boiling water. Like that's what I think of when I think of Celsius. I was like, oh, 20 is pretty low, but then I was like, boiling water means you would be like boiling in water, so maybe it's not a very good scale. It's because like in my American brain, it's like what I think is cold, like what I think is like really cold, right, is like 10 Fahrenheit. That's like a normal level of cold. Like you could still go out if it's 10, or if it's like 8 even. But then, like, the hottest you can get is, like, you know, the hottest that, like, I would want to go is probably, like, 95 Fahrenheit. Like, on a scale from this, I was like, oh, I don't know where 20 C is. It's probably, like, here. So, dumb American brain. But in reality, it's like, if I put this back, like, water boils, like, all the way over here. So 20 is more like here. Anyway. I digress. Okay, we don't really need to do anything silly then. Our wavelength is just gonna equal, 343 over 686. Oh. 1/2. So this is gonna equal 1/4 over 1 over 8 pi equals delta x. This is a silly song. Can I check it? What are we at? 23? Oh. That's not. That's not what I thought. Is this in meters? Wait. It's in meters. What's 1 over 8? What's 1 over 8 pi meters? I've never really thought about that. This times 100? Wait, no. Yeah. This music is making me insane. Okay, so that's definitely not right. Maybe I need to do 1.5? 25 centimeters. Okay, we're okay. The music switched. 25 centimeters. Huh. One over 8 pi is definitely not... Yeah, that's like 3. What if I did, instead of 0.5, I did 1.5? Let's try that. Yeah. So what is that? 3 halves times 1/2 is 3/4. 3 over 8 pi? Times 100. 11.9? That's still not right, though, is the thing. 11. Okay, wait. We can see what the thing is for this, actually. Because the one thing that's really nice is that my professor does is he does write out like solutions to the problems that he assigns. Just like, that's so kind. That's so kind. Or he finds them from the textbook. But it's so kind, so kind. Okay, the model of two waves depends on the interference. D equals lambda over 2. Wait, no, 2 pi, wait. Wait, this looks very similar to what I did. Which is good. Wait, it's 1/2 times... Wait. They're in phase, it equals 0. Yep, D represent path length difference. Using M equals 0 for the smallest D. Can I explain why hippos tend to have no fur? I think you'd be better suited to ask one of my animal science major friends for that, but, I can make up an answer for you. I think that hippos tend to have no fur because they like being smooth, and, I think, it's too hot where they are to have fur, so they probably evolved to not have fur. A block of mass M is suspended by a string of constant K. Wait, suspended by a string of constant K? What would a string need a constant for? Okay, sure. Which is attached to a string, which is itself attached to a ceiling. At t equals 0, the string... Wait. Wait a second. I just want to... Okay, this is what I'm imagining. Block suspended by a string of constant K. String. Which is attached to a string. Other string, which is attached to the ceiling. At t equals 0, the string is cut. Which string? What is the acceleration of the block immediately after the string is cut? Would that not be, like, just free fall? Would that not just be gravity? I'm so confused. First off, I don't know which string is cut. Second off, how is this not just a free fall problem? Like, unless it's like this. Unless it's like this. Then it's a different question, possibly. Because there's, like, tension, right? Makes sense, don't need fur to keep them warm? Hell yeah. Hell yeah! Okay, I'm gonna get rid of this, because they gave us the room temp, so I'll just do this. Just to clean it up a little bit. 343 over 686 equals 1/2. So the 1/2 is right, because it was asking for the smallest distance, right? So that's right. 2 pi d over lambda equals pi. Oh! Wait. Pi. Ah, okay. So that lambda equals 1/2 is... Okay, this is almost right. It's just this doesn't equal 1.5, this equals pi. Which makes sense, that makes sense. So then we have pi over 2 pi lambda. Cool. So then we get rid of this, and then we have lambda over 2 equals 1/4 meter equals 25 centimeters. It's behind my big head. There you go. There we go. Okay, so yeah, that makes sense. The phase difference would be in radians. Okay, I'm glad I looked that up. Alright. I don't know why I drew such a long line here. I guess because I wanted to do this, and then I didn't do that. You can do a little version of that. Wait, I need to make sure they're actually... $25. Let's hope it's a short problem, because I am running out of space. Oh, you have a question? If it's the same question, if you could clarify it, then I would definitely solve it. Okay, a pulley arrangement is shown in the figure. Oh no. Oh no, I don't know the figure. Let's see if I can do it. I'm gonna assume it's like what are they called? Somebody's machine. Their name starts with an A. Cylinder A has a diameter of 30 centimeters. The working handle? Oh. I remember, like, would it be like... Let me think how this would, like, make sense. If you have a handle, the direction of the winding on A... Oh, are the cylinders like the pulleys? Like, so it goes around this way, and it goes around this way, and there's like a handle here. So if you wind the handle this way, the rope goes this way, which the rope goes this way, and A turns this way? No, they turn different ways. I don't know. I can't do it without the diagram. Send me a link to the diagram. You can send links in chat. As long as they're fine. Otherwise I'll delete them. Ooh, what is the thinnest film of magnesium fluorine on glass that produces a strong reflection for orange light with a wavelength of 600 nanometers? Oh, okay, a strong reflector. I have a picture? Oh yeah, send it. Oh, is it in the Discord? Did I just not check it? Oh, maybe? Strong reflection. That's gotta be... Well, so we're still talking about interference, so... Strong reflection. reflection. Thinnest film on glass. Okay, let's draw a picture. So here we have glass. Here's our glass. Glass. And here's our film. What this is saying is we want to... How do I join the Discord? Here. You can put the image in the problems if you want. This is the film. So, for strong reflection, what we want is... I don't know what we... So, basically, like a light ray comes in. Oh, okay, so we're trying to find, I guess... something that makes the angle very small here, but away or towards the normal. Okay, so if we do this... Oh, I should probably not draw it directly coming at the normal. That's not how light works. There we go. Okay, so if we want this to reflect, we want not a lot of light to come through, which means that we want... Well, we can't change the glass. Oh, we want to change the... Okay, never mind. This is a really specific problem. I'm going to go and see if they have an example of it. I'm assuming they have to, like... There's an equation for it. Beats... nope. But we'll have to read that later. Designing an... Okay, yep. Designing an anti-reflection coating. Awesome. Magnesium fluoride is used as an anti-reflection coating on lenses. The index of refraction is 1.39. Reflection is minimized if the two reflected waves interfere destructively. It's the bottom question? Let's see. Whoa! Holy shit, okay. Let me yoink that. I'm gonna skip this question, by the way. Not this one, but the other one. A pulley arrangement is shown in the... Do I know how mechanical... Oh my god. Also, what does cat boy mean? I'm a boy who's a cat. I got big cat ears. And a tail. Oh, I do have a tail. Look, wait. You can see my tail. It's there. I got a tail. Normally you can't see it. I need to remake my model. I like the face a lot though, which is why normally I just... Over here. Oh god, I'm off screen. I'm so off the screen. I want to be more. I'll zoom out. I'll zoom out too. Can't be too big. Can't be too big. Gotta focus on the math. Okay. Do I know? Do I remember how to do mechanical advantage? Oh, I haven't done this in actually 5 years, I think. Advantage. Oh, input, okay, force input over force output, okay. So which way do you turn it, I guess? I guess if you turn it this way, then B turns this way, and C... You turn it this way, B turns this way, this rope goes up, this rope goes down, and A is wound the opposite direction. So if this rope goes down, then A turns this way. Have I seen a walrus in real life? I mean, I know like a walrus looks like... They look like this. It's my beautiful walrus drawing. I don't think I've seen one in real life. Maybe I have. At like a zoo when I was young. I'm trying to think. I've definitely seen like penguins. Are there any walrus in the Pacific Northwest? We have sea lions, which are not like walruses, but they are sort of like this. They look like this, and they have a lot of whiskers, and they have big fins, and flippers. So sort of like a walrus, but without the tusks. Walruses don't really have... walruses, I feel like, sometimes have whiskers, but these guys have a lot of whiskers. Sea hog. Oh yeah, manatees also. They're like this. They're like really big. Sea cows. Type in Google walrus at Scarborough. Oh, I think I've seen that walrus. Is that like the walrus who like was like getting on people's... Yeah, he was like getting on people's boats and stuff. Yeah. Oh, that's crazy. They're so big. That's like kind of scary. Okay, I don't know how to do this. I don't know how to do this question. Well, no, I do. I kind of do, but like I don't know how to do the math for it. I have not done this in a long time. Like, I don't even... I had to do... The last time I had to do mechanical advantage was when I was in 8th grade. I was in 8th grade. We had to do a, like a simple machine or whatever. And I made a... The only rule was that we couldn't make a catapult. So of course I made a catapult, but I turned it on its side. So it was like this, and it was a torsion catapult. So it was really strong, and like a torsion catapult works by like using the torsion of like a string. And you would wind it up and it sort of held it back like this. And there was just like this pencil that I like put in it to like stop it. It was really scuffed. But, and you would like wind it with this. It was a massive rod because it took so much torsion to like pull this thing back. And so you would wind it up, right? And it was it wasn't really like this. It was more wound like an infinity. That's not an infinity. It was wound like that. Like around the base a lot. And around this string. And you would pull it and you would wind it back, and then I would put like a starburst here, and the whole thing was I would just launch starbursts at people. Like that was the project, because we had to like present it, and I was like, oh, what can I do? But yeah, it was actually negative efficient. It would have like its efficiency. It took more force to do this than to just regularly throw the starburst like at people at the speed that the starburst was going. It was not a very good machine. I might still have it somewhere in a basement, but I don't think I do. I also... we had it on this, like, giant wooden board. Like, I don't remember why it was so big, but we only had a really big piece of plywood to put it on, so it was just, like, on this massive wooden board. Yeah, that was my experience with mechanical advantage. I was not really the best at that at the time, at least. Like in my design classes, we don't really, I mean, I guess I haven't taken statics yet, but we haven't talked about mechanical advantage in that way. So, you know, maybe it'll come back. Then again, we haven't really, like, I don't know, we don't talk about like screws as like simple machines or whatever. We're just like, this is a screw. This is how you call out a screw on a tolerance and stuff. More about like force analysis, I think, for statics. Anyway. Alright, what is this? 27. Let's hope it's not another thin film question. It's not. Okay. Oh boy. I'll take a picture of this, because it's a picture. Alright. So, it's asking for this picture. Are these waves in phase or out of phase? So, what this is saying... Well, okay. So this is emitting waves here. Oh, this went green. These are the waves from 1. And then these are the waves from 2. So these circles are representing the crests of the wave, right? So in between, we can imagine that those are the troughs. So we can see that right here, they're meeting up. Right, a crest is hitting a crest. And, but I think they are out of phase because that place where they're meeting up isn't here, right? Like if you look at the direct line between the sources, this crest is meeting up with the trough here. So I'm gonna say that they are out of phase. Oh, never mind, they're in phase. I lied. Yeah, so because they meet up here. Oopsies. Huh, that's fascinating. I guess maybe because they're the same size? Okay, make a table with rows labeled P, Q, and R. And columns labeled R1, R2, delta R, and CD. Fill in the table for that, giving the distances as multiples of lambda. Okay, so we'll do it like this. R1 equals, so R to 1. We're going 1, 2, 3. R from 2. 1, 2, 3, 4. Delta R equals lambda, which means that it's constructive. Nope, it's destructive. I lied. Wait, is that... Wait. Fuck. Nope, it's constructive. It's constructive. Wait, Q... Okay, Q. So R1... Right, 1, 2, 3.5. R2 equals 1, 2. Delta R equals 1.5, that is destructive. 1 equals 2.5. R2 equals 2. Nope, I counted the wrong one. 1, 2, 3, 5. Ah. Delta R equals 1. That's constructive. There we go. Oh, it looks like an E. Hello. Hello, Juice. I'm gonna call you Juice. It's a big yo. What's up? Okay, cool. CDC. Am I a math lad? A stats lad? I am an engineering lad. I do physics. I do physics and math and engineering sometimes, but less engineering because my drafting homework is not that interesting. I like it, but some people hate it. Okay, can I ask you a question? Sure. I will do my best to answer. I've not taken stats. If it's a stats question, I won't be able to answer. But if it is calculus, or if it is physics. We have multimodal distribution. No! Oh, it's stats! Oh, it's stats! Oh, I don't know if I can answer it. I will listen at the very least. Don't worry, it's not that bad. I kid you not, I have never taken like, I have never set foot in a stats classroom, but yeah. Okay, and we're sampling from it. You have multimodal distribution. Quickly Googles multimodal distribution. Is that multiple times? Okay. Ability with more than one mode. Oh, okay. I see. Say I get a result for one mode or whatever. From one mode, okay. Yeah, no, I want my other samples from the same mode. Okay. With a degree of variance, okay. Sure. Help? What? Is it like a code thing? Like what? I don't know what do you mean? Like how are you getting your samples, I guess? Is it like MATLAB? I don't... Yeah, or any math theory. I'm using... Oh, okay. Okay, so here's what you're gonna do, alright? You're gonna go to your favorite browser. You're gonna hit Command T. You're gonna search... Get samples from same mode, numpy, Stack Overflow, and then you're gonna hit Enter. And you're gonna see... Here, I'll get samples from same. You've tried that? Oh no! Okay, well, so first off, I've never used numpy. You can tell from the fact that I'm calling it numpy and not like numpy. Let's see. Let's take a look. I do know coding. That is more of my area of expertise. Googling things. Wait, why do you want your samples from the same mode? You need to know a theory? I don't know how, I don't know even where to start with that. I don't know, like, where do you put in the theory? There's a solution? I'm definitely not the best guy to ask for this, I will say. Okay, we have a distribution of heights. Now male and female are gonna be two nodes. Okay. Nodes, or modes? Oh. Modes. Okay, cool. Yeah, I know words. If I sample and get a male, I want to make my next sample also male. Okay. Now, when you get your samples, are you writing code to do that? Like how physically are you doing that? That's the part that I'm confused about. Because I know you're using a program, right? But I don't know how numpy works. Numpy has a built-in function to get a sample. Oh, okay. Can you input... Wait, let me just Google this shit. Let me see if I can look at a little bit about this. It's a library for Python. Okay. So you have how is your database set up? And you can search numpy kernel density. Scikit, okay. Got it. Okay, so it's... I see. Okay, this is definitely more, actually, something that I could help with, because it's code. Okay, I would say, like, the best bet you're gonna get is by trying to find someone else who's doing this, just because I don't know the libraries. But I will say, so, for your data, is it set up that, like, are the samples set up where you can access information about the samples? So, like, when you say, I want this sample, can you say, for this sample that I got, like, tell me the name, or tell me, you know, the age, or whatever? Is it like an object? Because what I worry is that there's nothing that's saying just a numerical value, yeah. So that's what I would worry about, because if you have like a mode, right, that you're getting because of a, like, extra, like, data, right, about this certain object. So let's say you have, like, a sample, I don't know, let's say you want, what you're looking for is you want, like, a bucket, right, that's saying, okay, here's the value, but also, like, maybe here's the position on the graph that it's at, like, that could tell you where the sample is, or here's the mode that it's a part of, or here's the, you know, here's some extra information about this sample. I can always resample until it's in a range, but that's terrible. I'm just wondering if you can actually, like, what I'm wondering is, I think you want something, and I don't know if that thing exists within the program. Do you know what I mean? Like, what you would, I think possibly, right? Because there's no way that this data that you have, there's no way that this data, this one little, because what you're looking for is, like, you want a bucket with lots of information. You have one piece of information, right? You want a bucket filled with lots of balls. You have one ball. There's no way that this is going to contain information about what mode it's a part of. It only is a ball, right? It only has that one value. This is just a number. The closest thing you might be able to do is, like, if you have a graph that you're, like, plotting stuff on, you might be able to identify the position of a node within a mode within a certain distance, right? And define that. And then you can use this value to say, okay, is this value within this, like, XY range or whatever? That's what I would say. Like, I think you said I can always resample until it's within a range, but that's terrible. I don't think that's that terrible. Because, like, if it's terrible... me. Beast got me for a sec there. It's fine. It's that's the curse. Don't worry about it. Sorry for assaulting your ears. I'm so sorry. I really need to fix this. I don't know why it happens. It just happens. Anyway, moving on past the psychic damage that I do every single stream at random intervals. I think that if the reason you don't want to do this is because you think it'll take too long for resampling, I don't think that's an issue. But if it has an issue with, like, you don't want to, like, you think that it'll be less accurate or something, like it's just, like, not including stuff, then I can understand that. But I think that it's, like, you want to use, I would say probably run through all your values, find a way to say, okay, we have a bunch of values that are clustered together, right? If it's, like, you know, all over the place and you have, like, a bunch of values here, right? Find a circle that's, like, bigger than this, and, like, you need to make sure that it's, like, a circle that includes all the ones you want it to include and doesn't include ones like this. Right, so there are algorithms for that, probably. The software uses performance sensitive, so I hate having the speed up to randomness. Well, okay, if you don't want to do randomness, then you could actually just go through, like, every single value, then, and just check. Because it wouldn't necessarily have to be... It wouldn't have to be random, but you are trying to, like, sample stuff, so in a way, I think there's already randomness involved. I do see what you mean, though. The title says interference pattern, say Fourier transform or something. No, but it's diffraction grating. A diffraction grating produces an interference pattern when wavelengths of light hit it. Like that. That's an interference pattern. Do diffraction on my grating till I interference pattern. You hated that? It's not that bad. I don't like doing interference like this. This is more annoying, in my opinion. I haven't done Fourier transforms. This is all based off of me going, here's a problem. I know how to code. What is logical? But yeah, I would say if you can figure out a way, either like, if you have a graph, it's kind of hard because I just don't know what information you have access to, you know? Like, there's probably a way for you to define a mode. That seems like it's more useful. Oh, okay. There's a function for that. Oh no, it takes out the most, that's just one. Define a mode. Look up Otsu's method. Oh, yeah. Yeah, I was gonna say you could do it with AI if you really had no other choice, but I really don't know, like, your restrictions, right? So, like, if I say... Because it's pretty easy to, like... Because I've worked on AI, like, image recognition stuff. If you had a graph that was, like, you know... If it was a histogram, right? Let's just say it's a histogram for whatever. You had a graph that was, like, something like this, you know... You could easily, very easily, train an AI to be like, there's something here, there's something here. Right? There are definitely AI models out there that, like, you would be able to hook into your project. And the question is like, there's a lot of questions. Are you looking for something that's completely automated from start to finish, also? Or do you want to have to be like, I'm going to put data in here, then I'm going to put data in here, you know, into this, and I'm going to take this result, and then I'm going to put it in here, and then it's going to give me something else, and then I'm going to put it in here. Like, I don't think that's what you want to do. So then there's a question of, okay, how do you integrate, like, an AI image recognition of a graph into NumPy, and then it gets harder. Because you could, if you have a data set that's, like, one data set, right? I don't know what you're using this for either. Is this like a class, like one problem? Is this a project that you're going to continuously work on? Because if it's something like if it's a report, right, and you've spent a long time, yeah, if I need a sample from mode A, you resample from mode A. Totally. You can do. I mean, there are a lot of different ways you could do that. Like. It's just the two problems you have are you need to define what mode A is, right? And you can either define that by hand, or you can define that by an algorithm, or you can define that by artificial intelligence if you want to use it visually from a graph, right? So we have to know what mode A is before we can do it. And then the second problem is you have to be able to sample directly from this. Right, because there's an algorithm that can give you an X value that differentiates between modes. Is that like the distance between modes? Also, can you specify can you specify sampling from a certain, like, X location? It will tell you where the two modes separate. Oh, so like this distance. Like that? Yeah, because I mean, if you could do that, then what you do is you take your data. Oh, draw a vertical line, like here. Yeah, it just tells you the distance to that line, right? I just didn't draw the vertical down. Because then what you do is you have your data, you run the, close enough, you run the thing that tells you that you get a delta X from the data, and then you sample all your data. Then you find if number is, you know, in delta X or past, and then for either one of those, then just sample from delta X, sample past delta X. But this assumes that you can sample over a certain section. This also assumes that you have a location of a point in the space. Although I think those are two assumptions that aren't that crazy to assume. Like, I don't know. I don't know if this is helpful or not. But this is how I would do it in terms of code. Interesting problem though. Yeah, it is really interesting. I think the hardest part about it is that I just don't know the limitations, or I don't know the limitations. I also don't know the powers that exist within the software, so it's sort of hard to think about it when you don't have constraints, because I'm thinking about this in a very basic, I guess, data science way, where it's like if you didn't really have anything. Thanks, anime. Yeah, no problem. I hope you figure that out. I at some point I will do NumPy or MATLAB work. I just haven't had to deal with all that yet, because we kind of got to do like, I mean, I think normally for engineering our I'll let you know if I do and you're still online. Yeah, feel free to I mean, if you want to join my Discord or just hit me up with a DM or whatever. Either or. Okay, I gotta draw this thing right. I need to see how they're drawing this. So for constructive, the crest of this is lining up with the trough of that. Okay, I'll slide in. Oh, here, let me give you a... There you go. If you want. No pressure. So for this one, then... to my DMs? Okay, got you. I have Twitter. I have, you know, other stuff. You can find my Discord on that. My DMs are open. And you can leave if you want after. I just don't want to drop my tag, because then I have to go all the way over there and get my tag. Let me see if this has a picture, because as picture solution. Oh shit. What? Okay, I could have drawn that easier. What? I didn't need to draw this garbage? That's sad. Okay. Fine. Fine. I didn't realize we didn't have to draw the circular waves. God damn. Okay. Here we go. 2 meters. And there's a point that they are both going to. There's a point in front of one of the speakers, which is 4 meters. Sorry, sources, they're not speakers. Perpendicular to the plane of the speakers. Is it a point of maximum constructive, maximum destructive, or something in between? Alright, so we gotta get a couple things. So R1, we'll call this one 1, we'll call this one 2. R1 is gonna equal 4 meters. R2 is gonna equal, well, it's a 3, 4, 5, it's not a 3, 4, 5 triangle, so this is gonna equal square root of 16 plus 4. Square root of 20. Which is, what, 2 square root 5 meters? That means delta R is going to equal 4 minus 2 square root 5. Wait, that's the bigger one. 2 square root 5 minus 4. Alright. So then we got to use our little equation, which is going to be delta, the difference in phase. Ugh. We don't know the difference in phase, right? So it's going to equal 2 pi times 2, square root of 5 minus 4. That's gross. Is that really that? That's nasty. Whatever. And we can use our frequency. V equals lambda f. Lambda equals V over f. So 343 over 1800. That's a lot. That's a very, very frequent wave. Wow. There's not really any nice way to write this. 0.1906. Okay. And then they are in phase, so that's gonna be plus 0. And then we just have to see if this is... I'm gonna guess it's not gonna be a nice number. Just, you know, off the top of my head. Just thinking out loud here. Just thinking out loud. I don't think this is gonna be a multiple of lambda. What is this? 2 pi? 2 root 5 minus 4. Then divided by 0.906. Yeah, that is 15.56. And that would have to be a multiple of pi, I guess? For that to be real, I think that's... Ooh, actually... Let me see. Oh, wow. Actually, they did do this out. Oh, because they put it in terms of... How do you... Oh, okay, get rid of the 2 pi. Got it. That's not it. That's 2 point... Wait, maybe if I do this. This is a finicky game to play. Nope, it's 2.477. I don't... Let me see if I do 2 root 5 minus 4. Oh, did I put it in... No? I put it in meters. 4 minus 2 root 5? Nope, that's not it. Why is that like that? Yeah, 0.472. I don't like that. I don't like that. Oh, wait, 340? Wait, what the heck? Why are they using sound to be 340? Is it not 343? Okay, this is I'm gonna be honest, this is kind of a not great problem, because I think it relies a lot on how you round, so I'm just gonna skip that one. Okay, let's do one more, and then we'll wrap up, because been a bit. And I also need to go do animation after this. Alright, there's my walruses. 30, yeah, we're skipping 30. 33 then. That's kind of, I don't like that. That's kind of gross. Maybe I'll do a different one of that same thing. That's okay. Okay. A flute player hears 4 beats per second. 4 beats per second when she compares her note to a 543 Hertz tuning fork, the note C. She can match the frequency of the tuning fork by pulling out the tuning joint to lengthen her flute slightly. What was her initial frequency? Okay, so the beat equation is not in here. Cool, I love it when they don't put things in the place that they should be. It's fine. Beat equation, beat equation. Little brown bat. Okay, beat is the difference between the two frequencies. Okay, the beat frequency is the number of beats per second. So we hear 4 beats per second, so our beat frequency, F beat, equals 4, equals F1 minus F2. So F beat, so 4 equals 4 to 3 minus something, right? F2. Or, as it should probably be F1. Because that's like her frequency. So then F1 equals 527? Oh, it does actually matter which one is which. Does it? No, we should put the bigger number. Nope, that's right, that's right, that's right. Yeah. Let's see. Is that right? 527. Yeah, nice. So yeah, however many beats you hear is however many hertz it's off, so. That's interesting. And a beat is like a modulation in the sound. I kind of doubt he's gonna ask a question on that, but you know, whatever. Alright, well, it's a little bit of a longer stream. It was nice to hang out with you guys for a little bit longer today. I'm gonna be back, what day is today? Sunday? I will probably be back, Tuesday? Yeah, I think Tuesday would be a good day, because that's the day before my midterm, so I'll probably be studying some more for this stuff, and I also have a lot of free time that day. And then I don't really know when next. Maybe Tuesday and Wednesday, if I'm up for it, but I don't know. I had some extra time, so. Wednesday's kind of rough though, because I think I'm doing other. What am I doing? Oh, I'm doing design stuff. I guess I could do CAD. No, I'm not doing design stuff. I need to do design stuff for Wednesday. Well, whatever. We'll figure it out. I'll see you guys on Tuesday. Okay. Have a lovely day, everybody. I hope you enjoyed a little bit of, very little bit of physics for the 2 hours I was live. But we did some, and we'll do more on Tuesday. So I'll see you guys then. Have a great start to your week. If you have a holiday tomorrow, I have a holiday tomorrow. I am so hyped for an extra day off. It's gonna be awesome. Okay, I'll see you guys. Oh, Umbra, you just got here. I literally was about to end stream. I'm so sorry. Oh. I streamed for like 2 hours though, Umbra. You can watch the VOD. It's good, I swear. I'm so sorry. No. Oh, I'm crying too, Umbra. I haven't seen you in so long. I feel like I never see you in my chat. Aw, I miss you in my chat. With all your gaslighting that you do. Oh god, people are texting me. I'm sorry. You got hit by a van? What? I'm running to Twitter. Dude, what? What? Hello? Wait. I thought, no! I hadn't! What? When? I have to get an MRI done soon? What? Dude, oh my god. I didn't see that. That was 10 days ago? Holy shit. That's insane. Are you okay? Oh my god. Dude, Twitter doesn't ever show me, like, the tweets I want to see. That's fucked up, dude. What? Oh my god. I hope you're okay. Yeah, Jesus Christ. Take it easy. I hope you've been taking it easy. I have some bad nerve damage. What? That's so... Oh my god, that's so... Been sleeping a lot? Good, 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 good. Jesus Christ. I don't even... That sucks. Damn. Holy shit. I can't believe I didn't see that. I mean, I thought I haven't seen you around, like, in a while. Like, it hasn't just been, like, the past 10 days. It's been, like, you know... Like, ever since I got back, to school. But then again, we haven't been playing Minecraft, so... That's probably why I see less. God damn. Well, okay, I will be streaming on Tuesday. What time? I don't know. Probably like 3? Probably 3-ish. So yeah, oh, and then I'll be back on Thursday, maybe? Tuesday and Thursday? Maybe. Depends on how early I get off my lab. Alright, well, I do have to go, because I have a thing I gotta go to, but, take it easy, man, Jesus Christ. Rest well. Hope you recover soon. I hope your MRI goes well. Oh my god, that's so crazy. Oh, man. Okay, I gotta end it. I gotta go. I'll see you guys. Bye, Umbra. Bye, everybody. I'll see you guys on Tuesday. Bye.